So we were just saying burning velocity is an important quantity. It depends here on thermochemical parameters. It's actually, I mean, it only depends on the fuel and the thermodynamic conditions. That's it, where, of course, the mixture is part of the thermodynamic conditions. So, but we said earlier, it is defined for flat, undisturbed flame, curvature, things like curvature, flame shape, and so on. External influences that must be considered, and that's what we want to do next. So first we talk about flame shape or flame dynamics, and then we talk about here these other effects like flame stretch. So we start out here with this field equation. I said this earlier. We call this the level set equation, or the G-equation. Is often used in modeling premixed flames. And so we said earlier, I mean, if I just look at let's say this is a flame. This is unburnt, this is burnt, you know, there's a velocity here. This whole thing is like 3D, and then the flame always burns normal to itself. It propagates normal to itself. But at the same time also, even if it's not burning, if there's a velocity, it carries the flame around, okay? So the change in position of the flame is the sum of these two effects. It's just the background velocity plus SL. That's what we said in 1D. We can write this for 3D also, where we say the change of the position of the flame is the velocity, background velocity here now, you know, as a three-dimensional vector, plus the burning velocity, but because the flame burns always normal to itself, we say the burning velocity times the flame normal vector, okay? So that's how this looks like. And then we can introduce this level set function G. The level set function is defined to be negative in the unburnt and positive in the burnt. That's it, okay? Really what the function is, you know, in the burnt and the unburnt, that doesn't matter, you know, it's arbitrary, you can choose whatever you like. But the point is, by my definition I just gave, at the flame itself, the function G is equal to 0, okay? So if I have a field now of G, you know, I have a value at every point in space, I can always tell you from this, it's in the unburnt, it's in the, you know, it's negative, it's in the burnt, it's positive, or if it's exactly 0, that's exactly where the flame front is, okay? So that's the, so we say at the flame, G is equal to G naught. And I said it's 0. You could also say, you know, at the flame it's 5. Doesn't really matter. But so I always say it's 0. G naught is always 0 for our purposes. And then on the previous slide we had the flame normal vector. The flame normal vector is basically the direction of the flame normal is then nothing else than the gradient of G. And because the normal vector has to be has to have unit length, we just divide this, so this is the direction, and we divide it by the magnitude of this gradient of G, and then this is also normalized to have unit length, right? And then we say there's also an arbitrary choice. The normal vector, it's normal to the flame, but it could point either towards the unburnt or it could point towards the burnt. We want it to point towards the unburnt. Again, it's it's a choice, and so that's why we have the minus sign here, because the gradient goes in the other direction. Because here it's large, the value of G is large, and here the value of G is small. Now, one definition for G that's often used is that of a distance function. So the value, the local value of G is just a distance to the flame, okay? And in the burnt, you know, is a positive distance, and in the unburnt is a negative distance. And so from this, then I can from this definition, I can derive an equation for G, and that is actually shown here. We take the substantial derivative of G. Substantial derivative means, or let's say, I put myself on the flame front. I sit on the flame front, and I move with the flame front. No matter what the flame front does, I just move with the flame front, okay? Then the change I see in the value of G is equal to 0, because I always sit at the flame front, where the value is always 0, okay? So that is the rate of change now that I see, that's what we call the substantial derivative, okay? That's the derivative, I mean the time rate of change, you know, in a coordinate system that moves with the flame, okay? And if I write this now in Cartesian coordinates here, in a coordinate system that is fixed in space, then the GDT is just here the partial dGdt plus dGdx, or the gradient of G, dGdx dx dt. Okay, and dx dt here, that's the speed of this flame. That's the local speed of the flame. But we said earlier the local speed of the flame is the background velocity plus SL times n. I can plug this in here, and then you see I get nabla G or del G times dot V. You know, that's this term. And I get a second term here, which is del G times SL times del G divided by the magnitude of G. Or here, let's say the normal vector dot del G. And here if I plug in the normal vector, I have del G dot del G. That's the magnitude squared divided by the magnitude, so 1 goes away. So that's the term that's left over. You put this on the right-hand side. That's the propagation term, and this is the convection term. And then you see we get an equation that looks, let's say, a little similar to let's say, a temperature equation, but it's not the same because it does not have a diffusion term. There's no diffusion term here, right? So the mathematical character is different from the temperature equation or species equation. And it's different, especially since that's the interesting thing. This equation is defined only at the flame surface. It's not defined anywhere else, right? Because it comes from this condition. The GDT at the flame surface is equal to 0. That's how we derived it, so it's not valid anywhere else. So if I solve this equation, it will always tell me correctly where the location G equal to 0 is, which is where the flame is, but everything else is wrong, you know? And it might be multi-valued and it might be numerically difficult. So that's why when we solve this equation numerically, maybe that's a side note here, we solve this numerically, we advance the equation and then we do a reinitialization where the entire field, the rest of the field is recomputed to, let's say, be a distance function. Okay, so the solution of this is a little complicated, but we know how to do this, and so maybe it's not so complicated after all. And so this here, I mean, we say the burning velocity is with respect to the unburned, and because of this, for consistency, this velocity is also the velocity, you know, on the unburned side. So if I sit on the flame, and the flame is infinitely thin, if I say, I mean, here we're treating the flame like an infinitely thin interface, then on the flame surface, I have two velocities. I have the unburned velocity and the burnt velocity, and they're different because there's a jump of the velocity across the flame front. And because this is with respect to the unburned, also this here has to be the velocity that's just on the unburned side. And one thing is interesting is that this, you know, flames, or especially this equation here, they form these cusps. If you see, if I have a, here at time 0, I have a flame that looks like this, and it burns normal to itself, then you see this curvature will get larger and larger, and until you get a cusp like this. And then, of course, in a real flame, you have now curvature, and the curvature gets very large, and that could make, for certain fuels, could make it burn a little faster here, so this cusp would go away if the burning velocity is a function of the curvature. But if if it's constant, then this is what you get. But it's not totally unphysical, because if you look at real premixed flames, that's how they look like. You always have very small or large regions of small curvature towards the unburned, and you have very large curvature towards the burnt. So if you look at the curvature distribution, let's say you do a measured curvature distribution of a premixed flame, then this is what you get. It's skewed to one side to have large negative, so we call this a negative curvature, this is a positive curvature, is to have very large negative curvatures. Okay, so but that, and then here's just an example for how to use this to look at a Bunsen flame, but we don't need to discuss this. Now, we said a few times flame stretch can be very important. With flame stretch, I changed this also maybe in your handouts. It's a little different, but what is flame stretch? Flame stretch is the relative rate of change of flame area. It's 1 over AD ADT, okay? So how does the flame area change with time? That's the flame stretch. And that is, of course, very important because if the flame area of, or let's say a consumption speed, how much fuel per unit time you burn depends, of course, on the flame area. If you have a lot of flame area, you burn much more than if you have small flame area. And so the stretch rate is therefore very important. And, you know, for example, so there are two effects that change the flame area. One is curvature, and the other one is strain. And, you know, two examples. Curvature, for example, look again at the case we had earlier. You have a spherical flame that has, you know, curvature, and it burns. Then, of course, it has positive curvature. Then the flame area gets larger, right? If you have curvature towards the burnt, then you know you have like a cusp that burns away, and that makes the flame area smaller. Okay, so curvature, you know, positive or negative can make the flame area larger or smaller. And then also strain. I mean, if I have a flame and I have tangential strain, I make I stretch it and I make the flame area larger, and vice versa. Also, if I have normal strain, so if I had a flame that here looked like this, I had a flame that looked like this, and let's say this burns basically in this direction. And then I have a strain here, I have a compressive strain like this. Then, you know, after a little bit, this would more look like this. So compressive strain also make it smaller. And I mentioned earlier, if I have tangential strain here like this, then of course I make it larger. And really it turns out the tangential strain, that's the most dominant part that makes flame larger apart then from these curvature effects. Again, maybe I can show this here also. So here this has positive curvature. If this burns a little longer, then it will look like this, and I make the surface larger. This one here, you know, will look like this later on, and it made the flame surface a little smaller. Okay, so it's curvature and strain. You know, let's keep that in mind. And so this then results in something like this. The stretch or the rate of change is SL times kappa and plus here this K, and this is the hydrodynamic strain, which is evaluated in some way, but it's just, you know, strain is just a velocity gradient. So people have studied this, and their analytic solution or asymptotic solutions here for one-step chemistry, large activation energy assumption, and then this is how they the effects of stretch affect the burning velocity. The burning velocity is then the unstretched burning velocity minus a term here that involves the curvature, and then plus a term here that involves the strain. And you see that we have this factor here, this proportionality factor L. That's what we call the Markstein length. It has the units of length because obviously here you have SL, here you have SL. The curvature is 1 divided by meter, so L has to have the dimensions of a length scale. You could look at L as basically, you know, the sensitivity. How much does the burning velocity change if I change the curvature. So I can say SL divided by SL0 is equal to minus L times kappa. Okay, and then if I look at DSL by DSL0 by the kappa, that's the sensitivity of the burning velocity with respect to kappa. That's just minus L, right? So that's kind of the sensitivity to of the burning velocity towards curvature. What's interesting is that this Markstein length, it can be positive or it can be negative. And if it's positive, then you see if it's positive, then positive curvature makes the flame burn faster and slower, because of the minus, and vice versa. Negative curvature makes it burn faster. And so if this is negative, then I get the exact opposite effect. And that's exactly what happens when we go from methane, for example, to hydrogen. I mentioned this earlier. Methane, the tip of the Bunsen flame, of this Bunsen cone, it burns faster. And because of negative, so there the curvature is negative. If this is positive, then this here becomes negative. So that's what the Markstein length is, and you see the Markstein length also gives you the proportionality here of the burning velocity with strain. And in general, I mean, this here is under some simplifying assumptions, but in general, one should ask the question: why is the sensitivity towards strain the same as the sensitivity towards curvature? And in fact, it's not the case. In reality, this Markstein length here is different from this, and we need to distinguish, or we can distinguish both of these, but under the assumptions that are made here in this analysis, they come out to be the same. This just shows the curvature again. Can be written like this, and this here, I mean, because the length scale, it's often made non-dimensional with a flame thickness, and then we call it the Markstein number. This is a non-dimensional ratio then. And then we can also look at the result from asymptotics for the Markstein length, or here for the Markstein number. And what's shown here is, we don't need to go into details, it's just a few aspects that are important. So here the gamma is a measure for the density ratio. And so you see the first term here, just involves the density ratio. So the density ratio is an important aspect for this, for the Markstein length, or the Markstein number. Secondly, the Zeldovich number is here. What is the Zeldovich number? You see that's a non-dimensional activation energy, basically here divided by a non-dimensional heat release rate, okay? Or let's say this is activation temperature, and this is the heat release rate, or also in terms of temperature. That's the Zeldovich number, and then also the Lewis number is important here. If the Lewis number is 1, you see that all of this here is 0. And if the Lewis number is larger than 1, all of this is positive, and if it's smaller than 1, it's negative. So this part here, obviously Lewis number, we haven't defined Lewis number. Lewis number is lambda over Cp. So that's basically the diffusion coefficient of thermal energy divided by rho d. That's the diffusion coefficient of mass of species. And so if these are the same, then so if species and thermal energy diffuse at the same speed or with the same diffusion coefficient, then this here is equal to 0, and all of this here is not important anymore. What I wanted to say is the point that the Lewis number appears here shows that this here depends on diffusion somehow, okay? Because it has the diffusion coefficients. But if they're same at 0, and then it can be larger or smaller than 1, for methane, this is slightly larger than 1, so it's positive. For hydrogen, this is smaller than 1, so it becomes negative. Okay, so this here is always positive. This here is positive or negative, and you see that if this is negative enough, you can make the whole thing here negative. Okay, so this is a result here. It was derived by here Matalon, Makowski, very, very famous papers, and Clavin and Williams, both of these very famous papers, introduces here the Zeldovich number, I mentioned this, Lewis number, and yeah, that's really not so important here. Okay, so then there's more discussion here in terms of the level set formulation here with curvature. We don't need to discuss this. But this here shows then, experiments or results from experiments and results from simulation that show the effect of stretch. And again, stretch can be either by curvature or it can be by strain. If we look at the experiment I showed earlier for the spherical vessel, then of course, you have curvature, and the curvature is then shown here. So this is the burning velocity, in this case here as B, with respect to the burned. That's why this value here is so high. And unburned, with respect to the unburned, is about a seventh of this, as I mentioned earlier. So then you're back to the values, here in the roughly 40, 50 centimeter per second we discussed earlier. But the symbols here show the experiment. And so the ignition happens, or, because of the spark, and just after ignition, the curvature is very high, okay? So this is the point just after ignition. And then while the flame grows, the curvature gets smaller, and so you move this way, and this here is roughly where either the flame moves outside the visible field, or in the spherical chamber where the pressure, where you start compressing the unburned gases, pressure goes up, and then you don't use the data anymore. So this goes up. It shows that, so the burning velocity gets larger, or let's say with higher curvature, the burning velocity is smaller. So that's shown here. High curvature, what did I say? High curvature, the burning velocity gets smaller. High curvature, because the minus curvature, the burning velocity gets smaller, okay, if this is positive. So this for methane is positive. And then on the right-hand side here, you see a different experiment where one uses a so-called counterflow flame. We'll look at counterflow diffusion flames later, but this is an experiment that's done by Professor Egolfopoulos at University of Southern California. They use a counterflow burner where you have a premixed stream coming from the bottom and a premixed stream coming from the top, okay? So, and then you have two flames, actually, because in the symmetry plane, the velocity is 0. At the nozzle, it's very high. So you get a deceleration towards the symmetry plane. And so the flame tries to burn inside the nozzle, but the closer it gets to the nozzle, the faster it is. So it finds a place where it wants to burn, okay? So, you do this then on both sides. And what they do is they change then the flow rates, which changes the strain that you get because of the counterflow. And so they measure then the burning velocity as function of the strain rate. And they do the same thing. They extrapolate to 0 strain. And here you see that the higher the strain, the higher also, in this case, the higher the strain, the higher the burning velocity. Okay, and this here shows now, what happens here between here some hydrocarbon fuel, propane in this case, and hydrogen. So here is lean propane flame, and so this is spherical flame again, and we see so this is what we got for the this is what we got for methane, okay, and then here there's an outwardly propagating spherical flame for propane, but it's the same thing, okay, positive Markstein number. But then if we go here to lean hydrogen flame, outwardly propagating, then you see the larger the curvature, the larger also the burning velocity becomes, right? And so this is interesting for, you know, I said earlier in internal combustion engines, you want to burn as lean as possible. That gives you super high, gives you better efficiency, okay? So, but the problem is, just after ignition, you get a very, very small flame kernel, and that flame kernel is pushed around by the turbulence and so on. So it's very weak, and you want something that burns very fast in the beginning. Now, for methane, in the very beginning, the flame speed actually is the lowest you get, you know, in the whole combustion cycle. So that's not very good for going to super lean conditions. But for hydrogen, in the very beginning, just after ignition, the burning velocity is super high. So hydrogen actually, you know, even this very small flame kernel, even if you're very, very lean, it will still burn stably because especially in the beginning, the burning velocity is high, and then later on, the burning velocity gets lower. And here's something you can actually do only in a simulation, is an inwardly propagating spherical flame, where you have a mixture, again, in the spherical vessel, and you ignite it on the outside, and then it burns towards the center, okay? And then, of course, the curvature is exactly reversed, right? You get negative curvature instead of positive curvature, and then you know, the outwardly, they go exactly in the opposite way. The inwardly go exactly the opposite way. Okay, so that's the flame stretch, and there are some interesting aspects that come out of this, especially when it comes to hydrogen. So this is a flame here, and let's say the flame is a little bit perturbed. You know, it's a flat flame, but then you perturb it a little bit, you have some, you know, corrugations here of this flame front. On top here is unburnt, on the bottom is burnt, and so this thing here burns from the bottom to the top. And if it burns all with the same burning velocity everywhere, you know, what we said earlier happens, you get these cusps on the burnt side, and here curvature gets smaller. But now, the burning velocity depends on the curvature, okay? And so, you know, so this is positive curvature. If you have positive curvature and positive Markstein length, then here the flame speed will be a little slower, and here it will be a little faster. That's methane. So what happens is you have a perturbation, but the perturbation goes away, you know, because here's a little slower, here's a little faster. Now, this is what happens for hydrogen. This, again, is our initially perturbed flame, but then for hydrogen, the Markstein number, because of the 1 minus Lewis term, so the Lewis minus 1 term, and the Lewis number is smaller than 1, so Lewis minus 1 becomes negative. And then this here, positive curvature, negative Markstein number or Markstein length with a minus sign. So for a positive curvature, this will actually be faster. So this here for hydrogen will burn a little faster. This here will burn a little slower. And after a while, this looks like this, right? The initial perturbation got stronger. And then, of course, the effect becomes even stronger. And so that's why it's an instability. So that's what we call then the thermo-diffusive instability, because it depends on the difference between thermal and mass diffusivity. And, you know, it leads to this instability. And this shows this here in some old 2D simulations. This is originally unperturbed flame, or with very small perturbation. Unburnt, this is burnt. And then all of a sudden you start forming these cells here, and then the cells grow and give you this, you know, these wild things. We'll discuss this in a lot more detail when we talk about hydrogen. We have a special topic on hydrogen, maybe in one of the last lectures. And this here is another one, a simulation, where we start out, again, on top is burnt, on the bottom is unburnt. Is lean hydrogen air mixture. we have a flow that comes from the bottom, and the flow is just fast enough to keep that flame in the domain. And then you see in the beginning, we have just very small perturbations, but these perturbations, they grow very quickly, and they form these weird structures here. You know, you get these fingers here, and you see the fingers, they move very fast, and then they merge together and so on. And what we see here is that these flames, just because of the instability, they burn, you know, 4 or 5 times faster than without the instability. So this is a huge effect. And what's interesting also is that this is a perfectly premixed fuel-air mixture, okay? And then you have a flame, and behind the flame is burnt. Because the equivalence ratio is the same everywhere, it should have the same temperature everywhere. So what's shown here is the temperature, but you see the temperature is not the same everywhere. In the burnt, you get regions which have higher temperature, they're a little more orange, and lower temperature, you know, they're a little more yellow. And you see especially the regions where you have the negative curvature, you know, you get these trailing low temperature regions. Isn't that interesting? Why, you know, if the equivalence ratio is the same, why is the temperature different? What do you think? This was tough enough to give me time to have some coffee. Trick question. Because the equivalence ratio is not the same. The equivalence ratio is the same everywhere in the unburned, but the instability, it demixes fuel and air. Okay? And you get in the burnt, you get regions which are locally rich, and you get other regions which are locally lean. And so the locally lean region, so you get in these regions of positive curvature, they are locally rich, and maybe that's part of the reason why they burn faster. And then in the negative curvature regions, they become lean. They become so lean that they extinguish, and that's why you get these long, trailing, low temperature regions. This is the same here for turbulent flame, and you see here, this is what we just assume unity Lewis number for all species. So hydrogen, we just assume it diffuses exactly the same as thermal energy. And then here's the real hydrogen flame, and we see this here is actually 3 times longer. This is 3 times shorter, which basically means that the consumption speed, the burning speed, is 3 times larger because of this. So we'll talk about this all later on when we talk about turbulent combustion. Okay, but thermo-diffusive instability is very important for hydrogen. And then there's another instability, it's the hydrodynamic instability, and that's an inherent instability. That's an instability that, you know, does not depend on the Lewis number, let's say. It's an instability that you always get just of the hydrodynamics of a flame. So what's inherent to a flame is a density jump or a density decrease. So if you have a density jump and a propagating flame, that messes up the velocity field so that you get an instability. Okay, that's just what it is. This is how this looks like. Again, we start out with a flat flame and then we perturb it just a little bit. So this is the perturbed flame. On the left side is unburned. On the right side is burnt. And now you see you have a streamline here and it goes in the flame, and because of the heat release, we said earlier, it's deflected because of the heat release. So this here is deflected, you know, to converge here in a region like this. So it's deflected towards this side, and so that's why the streamlines converge here. If the streamlines converge, you form a locally higher pressure, and that decelerates the flow just ahead of the flame here. And so just ahead of the flame, if the flame here is, if the speed here is slower, then the flame actually, with the same burning velocity, burns a little faster in this region, and here it's a little faster, so here it burns a little slower in this region. So that's why an original perturbation, again, you know, this goes faster in this direction, and is slower, which makes the effect even worse, you know, the whole bending of the streamlines and so on. And so this is why, you know, this also forms instability. And that's interesting because, again, there's an inherent instability. It's always there. And the only way so why are flames not always unstable? Because it's stabilized by the diffusive effects, okay? And so we can look at this. We can look at this in the equations. This I just explained. So one can do a stability analysis, linear stability analysis, and get a so-called dispersion relation. The dispersion relation tells you what is the growth rate of an initial perturbation depending on the wave number, okay? So I impose a certain wavelength or wave number, and then, you know, I look at how fast does this grow. So that's what this dispersion relation tells you. And you see here, if forget about diffusive effects. So let's assume here the Markstein number is 0. Then all of this here goes away. You know, it's just this 1, and then I have only this first term here. And so this means the growth rate is proportional to the wave number. Wave number is just the inverse of the wavelength, right? Or basically tells me how many waves do I have per meter. So high wave number means basically high frequency, or wave number is in space the same as frequency in time, okay? You know, how many waves do I have per meter and not per second? And so, so it's proportional to the wave number, and you see that is this line. So all wave numbers are unstable. There's also no length, because if I assume the flame is infinitely thin, then, you know, there's no length scale anymore either. I mean, all I have here is just instability. But then you see you have these terms here, which can become negative. So this is when diffusion becomes strong enough and the Markstein number is positive, then it's a stabilizing mechanism. We saw this earlier, that stabilizes the instability. So now you get basically the opposite of the thermodiffusive instability, a thermodiffusive stabilization mechanism. And if that is stronger than this hydrodynamic instability, then the flame is stable. Okay, so that's what happens here. So you see for very small wave number, this effect here, it becomes small. Very small wave number, these go away. And then here it goes to, I mean, this diffusive stabilization is small. And so, but for very large wave number, this here becomes large. And then you see here the growth rate is negative, which means it's actually a stabilization effect. So for any non-zero Markstein, positive Markstein number, I always get somewhere a wave number above which this is stable, okay? And so that means, yes, flames are always unstable, but only on a relatively large scale. If I have a small flame, then I'm somewhere here on the right side of the point where it becomes stable. So this here would be the stable region, this is the unstable region. And so then the diffusive effects, they stabilize the hydrodynamic instability. But if you go to high pressure, for example, high pressure flames, then you know, the hydrodynamic, because the flame gets thinner and thinner, then diffusive effects become less important and hydrodynamic effects more important. So if you go to high pressure, then basically all flames become unstable. So that's why it's very difficult to measure flame speed at very high pressures, because I showed you earlier, we have this spherical flame, and it looks very stable, but you go to high pressure, you start forming cells on the surface, and it becomes unstable. And then, of course, I can't measure the burning velocity anymore. Okay, so I think all these things I just said already. So I said this is the result of a stability analysis, and here these next slides, they just show the stability analysis. And so you know, if you're interested in this, and again, you can sleep tonight. You have enough slides here that you can look at. And with this, I think this was the section here on kinetics next then, we will look at the effects of flame at flame structure. If I'm not wrong, should be a break now, right?